Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel, and today's topic of discussion is series resonant circuits. Our objective is to examine the phenomenon of resonance in series AC circuits and discuss electrical properties at resonant and at other than resonant conditions. As it is often said, never try to wrestle a pig. Not only will you get dirty, the pig will enjoy it. In this spirit, I do not intend to take the topic of resonance to the mat, but rather strike it viciously over the head with a long-handled coal shovel and walk away. As such, this lecture will present only the most important properties of resonant circuits and will intentionally avoid any entanglement with the dirtier aspects of resonance. If you are looking to get dirty, this is not the time nor the place. The idea is to present resonance in a clean, focused, and direct manner and walk out of this lecture without a spot on us. Let us begin. This lecture operates under the presumption the viewer is intimately familiar with fundamental series AC circuit properties, as illustrated in the Series AC Circuit Analysis lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or you only dimly recall its contents, please take the time to do so now. As you are no doubt aware, capacitors and inductors are essentially mirror images of one another in terms of electrical properties. The complex impedance of a capacitor is 1 over 2 pi FC at an angle of negative 90 degrees, whereas the complex impedance of an inductor is 2 pi FL at an angle of positive 90 degrees. At low frequencies, capacitors present high impedances, and at high frequencies, capacitors present low impedances. Conversely, at low frequencies, inductors present low impedances, and at high frequencies, inductors present high impedances. Current through a capacitor leads voltage across it by 90 degrees, whereas current through an inductor lags the voltage across it by 90 degrees. Capacitors are said to supply negative reactive power, whereas inductors are said to consume positive reactive power. I've heard it said that capacitors taste like chocolate and inductors taste like vanilla. In every conceivable manner, capacitors are the opposite of inductors, and inductors are the opposite of capacitors. Resonant circuits take advantage of this equal and opposite nature. When taken in series or inline combinations of the three basic elements, resistors, capacitors, and inductors in any order, Z total, the total impedance of the complete series circuit, can be calculated as the summation of individual complex impedances, where Z total equals ZR plus ZC plus ZL. Given the opposing vertical imaginary components of the capacitive and inductive impedances, these reactive elements essentially serve to moderate and or counteract the other's influences. It stands to conjecture there may be occasions in which there exist equal yet opposite amounts of capacitive inductive contributions that entirely cancel one another out. This is known as a resonant condition, where the magnitude of ZC equals the magnitude of ZL. Again, the resonant condition happens only when the magnitude of capacitive impedance equals the magnitude of inductive impedance. Odd things happen at resonance, only some of which I'll explain today in this sanitized lecture. Up until this point, we've been performing series AC circuit analysis at fixed frequencies. This isn't always the case, and frequency can and does change. As we've discussed, there exists some frequency at which the capacitive impedance magnitude equals the inductive impedance magnitude. If we overlay the plots of capacitive and inductive impedance magnitude as a function of frequency with each other, the resonant condition is readily identifiable as the intersection point of the two impedance curves. The resonant frequency, FR, is that excitation frequency that satisfies this condition. If you are as mathematically competent as I expect you to be, solving for the resonant frequency given fixed component values should be well within your reach. Resonance is achieved when the magnitude of ZC equals the magnitude of ZL. Note I've ditched the angles because we are not concerned with angles. All we care about is impedance magnitude. I am well aware capacitors have an impedance angle of negative 90 degrees and inductors have an impedance angle of positive 90 degrees and exist in perfect opposition to one another. Given this opposing nature, the capacitors and inductors' contributions towards total impedance will cancel each other out when their magnitudes are equal. Given fixed component values, we are being asked to solve for the frequency that satisfies this condition. When ZC equals 1 over 2 pi FC and ZL equals 2 pi FL, solve for the variable F. If you're feeling up to the challenge, by all means, pause the lecture and try this on your own. If you're tracking, you should obtain the following formula. By isolating F on one side, we ultimately get a workable formula. However, it's admittedly a little ugly. We can clean this formula up with the following additional algebraic manipulation. Given fixed component values, the resonant frequency is achieved at 1 over 2 pi times the square root of the inductance times the capacitance. You are free to use this simplified formula, or to derive it on an as-needed basis via algebraic manipulation. Importantly, you need to be aware that the resonant condition is an occasion in which the excitation frequency is such that the magnitude of Zc equals the magnitude of Zl. At the resonant frequency, odd things occur. Allow me to demonstrate. Consider the following series circuit consisting of a 100 ohm resistor, a 12 microfarad capacitor, and a 480 millihenry inductor. The source has an effective value of 120 volts and an excitation frequency that can be varied up to 200 Hz. What's the resonant frequency for this circuit? By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following value. Resonance is achieved when the magnitude of Zc equals the magnitude of Zl. Substituting our given values into the resonant frequency formula yields a resonant frequency of approximately 66.3 Hz. Let's check our work. The complex impedance of the 100 ohm resistor is 100 ohms at an angle of 0 degrees. At an excitation frequency of 66.3 Hz, the complex impedance of the capacitor will be roughly 200 ohms at an angle of negative 90 degrees. At an excitation frequency of 66.3 Hz, the complex impedance of the inductor will be roughly 200 ohms at an angle of positive 90 degrees. At the resonant frequency, the capacitor and inductor do indeed present impedances of equal magnitude, yet of opposite polarity. Let's now examine electrical properties like total impedance, current, and voltage distribution within this series circuit at conditions of resonance. Be on the lookout for bizarre or unexpected phenomenon. Let's first look at total impedance. The total impedance for this series combination of three elements at the resonant frequency is Zr plus Zc plus Zl. Substituting our given values, we find total impedance to be 100 ohms at an angle of 0 degrees. It appears as if Zc and Zl, being equal in magnitude yet of opposite polarity, effectively cancel each other out, such that the source is under the impression that the circuit consists of only the resistive component. Let's now examine current through this series resonant circuit. Given the total impedance has an angle of 0 degrees, we're probably safe to assume that source current will be in phase with supply voltage. Let's see if this is the case. An application of Ohm's law demonstrates source current will be supply voltage over total impedance. Substituting in our given values, we find source current to be 1.2 amps at an angle of 0 degrees. A phase shift of 0 degrees indicates source current is indeed in phase with supply voltage as we anticipated. Given this is a series circuit, it can be said 1.2 amps at an angle of 0 degrees flows through all three elements forming this series circuit. IR equals 1.2 amps at an angle of 0 degrees, as does IC and IL. Let's now examine voltage distribution within this series circuit. Prepare yourself for the oddest of odd behaviors. An application of Ohm's law demonstrates the voltage across the resistor will be equal to the current through it times the resistive impedance. Substituting our given values yields VR to be 120 volts at an angle of 0 degrees. The phasor diagram illustrates current through the resistor will be in phase with the voltage across it. It's worth noting at conditions of resonance, the voltage rise induced by the source appears to be entirely dropped across the resistor, leaving nothing for the reactive capacitor or inductor. Or does it? Another application of Ohm's law demonstrates voltage across the capacitor will be equal to the current through it times the capacitive impedance. Substituting in our given values yields Vc to be 240 volts at an angle of negative 90 degrees. The phasor diagram demonstrates current through the capacitor leads the voltage across it by 90 degrees. Similarly, yet another application of Ohm's law demonstrates voltage across the inductor will be equal to the current through it times the inductive impedance. Substituting in our given values yields VL to be 240 volts at an angle of positive 90 degrees. The phasor diagram demonstrates current through the inductor lags the voltage across it by a relative 90 degrees. Before we move on, it's probably worth a moment of your time to copy these results down at resonance or make a screenshot for later reference. The voltage across the reactive components at resonance is worthy of some comment. At conditions of resonance, not only are the voltage differentials across the capacitor and inductor equal in magnitude and of opposite polarity, these differentials have the potential to be astro-freaking-nomically huge. Look at that, 240 volts, twice that induced by the 120 volt supply for this particular circuit. While not every series resonance circuit exhibits such a dramatic increase in voltage across the reactive elements, this is one of the defining features of series resonance circuits that I find that makes them so interesting. Such a dramatic voltage boost across the reactive elements might seem a violation of common sense. However, Kirchhoff's voltage law, which states that the sum of voltage rises must equal the sum of voltage drops, still holds true. The Kirchhoff's voltage law equation for this series loop demonstrates that E equals VR plus Vc plus VL. Substituting in our given values, accounting for not only magnitude and phase shift, we find Kirchhoff's voltage law is indeed satisfied and our faith in an orderly and predictable universe restored. The key to the resonant condition is of course accounted for the equal and opposite natures of the reactive capacitor and inductor. Given voltage across the capacitor has a phase shift of negative 90 degrees and voltage across the inductor has a phase shift of positive 90 degrees, they are plus or minus 180 degrees or completely out of phase with one another. When voltage across one reactive component peaks, the voltage across the other reactive component valleys and vice versa. What's really happening at conditions of resonance is that reactive power is pulsating back and forth between the reactive elements inside the circuit. Sometimes this internal interchange of reactive power can be surprisingly large, as in this example circuit. Take a moment to consider just some of the fabulous events that occur at conditions of resonance. At conditions of resonance, the impedance magnitude of the capacitor equals that of the inductor, yet is of opposite polarity. Capacitive impedance has an angle of negative 90 degrees, and the inductive impedance has an angle of positive 90 degrees. Taking into account not only magnitude but also direction, they effectively cancel each other out. At conditions of resonance, total impedance is equal to solely the resistive component, ZR. At conditions of resonance, source current is in phase with supply voltage. Finally, at conditions of resonance, voltage across the reactive capacitor and inductor are perfectly out of phase with one another, and all of supply voltage appears to be dropped across the resistor. Given the right setup, voltage across the reactive elements at conditions of resonance has the possibility of becoming extremely large. These phenomena, as miraculous and wondrous as they are, only occur at the condition of resonance. At any frequency other than the resonant frequency, the magic simply doesn't happen. For us to appreciate the resonant condition in all its wonder, we need to examine the same circuit at conditions of other than resonance. For example, consider the following two scenarios. Scenario 1. Excitation frequency is reduced to 30 Hz, less than half the resonant frequency. How will this affect impedance, current, and voltage distribution in the series circuit? Scenario 2. Excitation frequency is increased to 120 Hz, just shy of 2 times the resonant frequency. How will this affect impedance, current, and voltage distribution in the series circuit? As an exercise, the viewer, I invite you to solve for the total impedance, the source current, and voltage across each component for these two scenarios. Given your previous experience with series AC circuit analysis, this should be the easiest of tasks. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. At a reduced excitation frequency of 30 Hz, this is an entirely different series circuit because the impedance of the reactive capacitor and inductor change. If excitation frequency decreases, capacitive impedance will increase, and inductive impedance will decrease. As such, we should expect this series circuit to exhibit slightly capacitive nature. Let's see if this is the case. The resistor is immune to the effects of frequency, and as such remains an impedance of 100 ohms at an angle of 0 degrees. At a reduced excitation frequency of 30 Hz, the 12 microfarad capacitor now presents an impedance of approximately 442.1 ohms at an angle of negative 90 degrees. As we expected, capacitive impedance went up. At the reduced excitation frequency of 30 Hz, the 480 millihenry inductor now presents an impedance of approximately 90.5 ohms at an angle of 90 degrees. As we expected, inductive impedance went down. Total impedance is the sum of ZR plus ZC plus ZL. Substituting our given values yields total impedance to be 365.6 ohms at an angle of negative 74.1 degrees. As we expected, total impedance is swung into the capacitive quadrant given the negative impedance angle. An application of Ohm's law demonstrates source current will be 328.3 milliamperes at an angle of 74.1 degrees. Source current appears to lead supply voltage by 74.1 degrees. Given the leading phase angle, the circuit appears to be largely capacitive. Given this is a series circuit with a single path for current, it can be said 328.3 milliamperes at an angle of 74.1 degrees flows through all three elements, forming the series connection. IR equals 328.3 milliamperes at an angle of 74.1 degrees, as does IC and IL. Let's now examine voltage distribution within this series circuit at the reduced excitation frequency of 30 Hz. An application of Ohm's law demonstrates voltage across the resistor will be 32.8 volts at an angle of 74.1 degrees. Current through the resistor is in phase with the voltage across it. Another application of Ohm's law demonstrates voltage across the capacitor will be equal to 145.1 at an angle of negative 15.9 degrees. Current through the capacitor leads the voltage across it by a relative 90 degrees. Finally, yet another application of Ohm's law demonstrates voltage across the inductor will be equal to 29.7 volts at an angle of 164.1 degrees. Current through the inductor lags the voltage across it by a relative 90 degrees. By the way, if you did not get these results, you are simply not qualified to discuss series resonance because you're still struggling with series AC circuit analysis. If this describes your sorry state, by all means get out of here and go hit up the series AC circuit analysis lecture, available at the Big Bad Tech channel, and come on back after you've got these concepts down. Take a moment to weigh the consequences of reducing excitation frequency below that of the resonant frequency. Capacitive impedance went up. Inductive impedance went down. Total impedance seemed to shift towards a somewhat capacitive nature. Source current went down and started leading supply voltage. Finally, voltage distribution within the series circuit changed. Less voltage was dropped across the resistor and inductor, and more was dropped across the capacitor. In summary, at excitation frequencies below the resonant frequency, this series circuit appears more capacitive. More on these observations in a moment after we consider the electrical properties of this same circuit at an increased excitation frequency of 120 Hz, just shy of 2 times that of the resonant frequency. At an increased excitation frequency of 120 Hz, just shy of 2 times the resonant frequency, this is an entirely different series circuit because the impedance of the reactive capacitor and inductor change. If excitation frequency increases, we should expect the capacitive impedance to decrease and inductive impedance to increase. As such, we should expect the series circuit to exhibit a slightly inductive nature. Let's see if this is the case. The resistor is immune to the effects of frequency, and as such remains an impedance of 100 ohms at an angle of 0 degrees. At an increased excitation frequency of 120 Hz, 12 microfarad capacitor now presents an impedance of 110.5 ohms at an angle of negative 90 degrees. As we expected, capacitive impedance went down. At the increased excitation frequency of 120 Hz, the 480 millihenry inductor presents an impedance of 361.9 ohms at an angle of positive 90 degrees. As we expected, the inductive impedance went up. Total impedance is the sum of ZR plus ZC plus ZL. Substituting in our given values yields total impedance to be 270.5 ohms at an angle of positive 68.3 degrees. As we expected, total impedance has swung into the inductive quadrant given the positive impedance angle. An application of Ohm's law demonstrates source current will be 443.5 milliamperes at an angle of negative 68.3 degrees. Source current lags supply voltage by 68.3 degrees. Given the lagging phase angle, the circuit appears to be largely inductive. Given this is a series circuit with a single path for current, it can be said 443.5 milliamperes at an angle of negative 68.3 degrees flows through all 3 elements forming this series connection. IR equals 443.5 milliamperes at an angle of negative 68.3 degrees, as does IC and IL. Let's now examine voltage distribution within this series circuit at the increased excitation frequency of 120 Hz. Application of Ohm's law demonstrates voltage across the resistor will be 44.4 volts at an angle of negative 68.3 degrees. Current through the resistor is in phase with the voltage across it. Another application of Ohm's law demonstrates voltage across the capacitor will be equal to 49 volts at an angle of negative 158.3 degrees. Current through the capacitor leads the voltage across it by 90 degrees. Finally, yet another application of Ohm's law demonstrates voltage across the inductor will be equal to 160.5 volts at an angle of 21.7 degrees. Current through the inductor lags the voltage across it by a relative 90 degrees. Again, take a moment to weigh the consequences of increasing excitation frequency beyond that of resonant frequency. Capacitive impedance went down. Inductive impedance went up. Total impedance seems to favor a somewhat inductive nature. Source current went down, and current started lagging supply voltage as we'd expect for a largely inductive circuit. Finally, voltage distribution within the series circuit changed. Less voltage was dropped across the resistor and capacitor, and more was dropped across the inductor. In summary, at excitation frequencies above the resonant frequency, this circuit appears more inductive. Let's compare and contrast the information we've thus far collected. Granted, we've got data for only 3 operating conditions, but a pretty obvious pattern should be emerging. If you think about it, the resonant condition represents kind of a peak condition, in which the series circuit appears as neither capacitive nor inductive because the equal and opposite natures of these reactive elements effectively cancel each other out. At frequencies less than the resonant frequency, the circuit appears more and more capacitive, whereas at frequencies greater than the resonant frequency, the circuit appears more and more inductive. Importantly, source current seems to peak at the resonant condition, as does voltage across the resistive component. Let's add this to our resonant condition properties checklist. At conditions of resonance, we should expect to observe the following properties. First, the impedance magnitude of the capacitor equals that of the inductor, yet is of opposite polarity. Next, total impedance will be equal to solely the resistive component, ZR. Next, source current will be in phase with the supply voltage. Next, voltage across the reactive capacitor and inductor will be equal in magnitude, yet perfectly out of phase with one another. At times, the voltage across these reactive elements can be exceedingly high. And finally, source current will achieve a maximum magnitude at conditions of resonance. Related phenomena are associated with the last important observation. Given voltage across the resistor is directly proportional to the current through it, we should also expect voltage across the resistor to also peak at the resonant frequency. And finally, given power is a product of voltage and current, this condition of peak voltage and peak current and no phase shift between voltage and current obviously represents a condition of peak real power delivery to the resistor. In fact, this is an extremely practical application of resonant circuits. Only at the desired resonant frequency will the device operate at peak power. Let's see if these observations hold true for a wide range of frequencies. As an exercise to the viewer, I invite you to solve for source current and voltage across each element at 1 Hz up to 200 Hz in 1 Hz intervals. Go ahead and pause the lecture and do so now. Just kidding. This is obviously a lot of tedious busy work best suited for a computer. In fact, the analysis of resonant circuits is one of the rare occasions in which I find a computer simulation to actually be better than a hardware lab simply because of all the tedious busy work involved. Many software-based circuit simulators offer a frequency sweep or a Bode plotter, where the software simulator varies excitation frequency from a user-defined low to a user-defined high. The simulator then plots the electrical properties for the circuit of interest for the desired frequency range. Perhaps the most important properties we can examine over a range of excitation frequencies are the following: total impedance magnitude as a function of frequency, total impedance angle as a function of frequency, source current magnitude as a function of frequency, source current phase shift as a function of frequency, and finally voltage magnitude across each component as a function of frequency. Let's start by looking at the plot of total impedance magnitude as a function of frequency. Total impedance magnitude appears to bottom out at the resonant frequency, in this case 66.3 Hz, right about here, where total impedance equals only the resistive contribution of 100 ohms. It makes sense. Given current magnitude is expected to peak at resonant conditions, it stands to conjecture that the total impedance magnitude, or opposition to current flow, would vary at this same operating point. Let's now consider total impedance angle as a function of frequency. At frequencies less than the resonant frequency, the circuit appears more capacitive and total impedance angle will be negative. At conditions of resonance, in this case 66.3 Hz, right here, the series combination of 3 elements appears to be neither capacitive nor inductive, and total impedance angle will be 0 degrees. At frequencies greater than the resonant frequency, the circuit appears more inductive and total impedance angle will be positive. What you get is kind of this negative 90 degrees to positive 90 degrees swoop passing through 0 degrees at the resonant frequency. Let's now consider source current magnitude as a function of frequency. Given a constant input voltage, source current magnitude will effectively be the inverse of the plot of total impedance magnitude as a function of frequency. It makes sense. Source current will peak at resonance because impedance magnitude valleys. The plot of source current phase shift as a function of frequency looks almost like a mirror image of total impedance angle as a function of frequency. At frequencies less than the resonant frequency, the circuit appears more capacitive and source current leads supply voltage with a positive phase shift. At conditions of resonance, in this case 66.3 Hz right here, the series combination of 3 elements appears neither capacitive nor inductive, and voltage and current will be in phase with one another with a 0 degree phase shift. At frequencies greater than the resonant frequency, the circuit appears more inductive and source current lags supply voltage with a negative phase shift. What you get is kind of this positive 90 degree to negative 90 degree swoop passing through 0 degrees at the resonant frequency. Before we examine the remaining plot, I'm encouraging you to take some time to get a good feel for these first 4 plots. Data presented in each plot and each plot's connection to all the other plots should make sense on a very basic fundamental level, and if it doesn't, I'm recommending you pause the lecture and stare at these plots without blinking until they do. My advice is to divide each plot into 3 parts: left, center, and right. Left. At frequencies less than resonance, source current will be smaller and lead supply voltage because total impedance is higher and it's a negative angle due to its more capacitive nature. Center. At the resonant frequency, current peaks because total impedance magnitude valleys. Source current is in phase with supply voltage because total impedance has a 0-degree angle. At regions close to the resonant frequency, you'd kind of get an approximation of these effects. Right. At frequencies greater than resonance, source current is less and lags supply voltage because total impedance is higher and has a positive angle due to its more inductive nature. This should be making sense. Let's now examine voltage magnitude across each component as a function of frequency, starting with the resistive component in red. This plot is pretty easy to explain. Given resistance is fixed, and we've previously demonstrated that current varies as a function of frequency, the voltage across the resistor as a function of frequency is almost identical to the plot of current magnitude as a function of frequency. Voltage across the resistor peaks at the resonant frequency. Let's now consider voltage across the capacitor in green as a function of frequency. At low frequencies, the capacitor dominates the total impedance and drops the majority of supply voltage. As current increases, voltage across the capacitor increases and peaks near, not necessarily at, the resonant condition. At increasing frequencies, the capacitor drops less and less voltage. Essentially, the opposite holds true for the inductor in orange. At low frequencies, the inductor drops very little voltage. As current increases, voltage across the inductor increases and peaks near, not necessarily at, the resonant condition. At increasing frequencies, the inductor drops the majority of supply voltage. Again, it's worth a moment of time to consider the importance of each curve and their relationship to one another. Again, divide this plot into 3 sections: left, center, and right. Left. At low frequencies, the capacitor presents the largest impedance and drops the majority of supply voltage. As such, there's not a lot of voltage left over for the resistor and inductor. Center. Voltage across the resistor peaks at the resonant frequency. Importantly, voltage across the capacitor and inductor at conditions of resonance are equal in magnitude, yet perfectly out of phase with one another. Right. Conversely, at high frequencies, the inductor presents the largest impedance and drops a majority of voltage. As such, there's not a lot of voltage left over for the resistor and capacitor. What's especially satisfying about these general purpose plots is that if you understand these general purpose plots on every level that I'm asking you to do, you by extension understand fundamental behavior for all series resonant circuits. Long story short, all series resonant circuits experience peak current magnitude at the resonant frequency. If you don't hit the target, the magic will not happen. Compare and contrast the plot of current magnitude as a function of frequency with these plots for 2 additional circuits, circuit X on the left and circuit Y on the right, plotted on the same scale as our original circuit in the center. Yes, the character of these additional plots may appear subtly altered, but if you think about it, they're all permutations of the same general purpose plot of current as a function of frequency. Circuit X's plot of current as a function of frequency appears to be squashed, spread out, and weakly defined. In contrast, circuit Y's plot of current as a function of frequency is clear, sharp, and distinguished. Our original circuit is kind of a mix of both plots. This being said, current for all 3 circuits still peaks at the resonant frequency. At the resonant frequency, we'd again expect voltage across the capacitor and inductor to be equal in magnitude, yet completely out of phase with one another. Really, the only thing left to discuss about series resonance is all the admittedly esoteric math associated with quantifying the shape of current as a function of frequency. Ideally, we should be able to come up with a handful of quantifiable properties that allow an individual to quickly ascertain if the circuit under inspection possesses a clear and distinguished response, as in circuit Y, or a muted and soft response, as in circuit X. Perhaps the most distinguishing differential between our 3 examples is behavior at or near resonant conditions. You note a pretty wide region of frequencies to the left and right of circuit X's resonant frequency yield almost indistinguishable results. A couple hertz to the left or right really wouldn't matter one way or the other, as source current inside this wider band doesn't change very much, as evidenced by the shallow slope. It can be said that circuit X operates at peak power conditions inside a very wide, extremely permissive band. This is in direct contrast to the behavior of circuit Y at or near resonant conditions. 1 or 2 Hz on either side might still yield desired results. However, any further departure from resonant frequency and one quickly falls off the edge of a very, very steep cliff. It can be said that circuit Y operates at peak power conditions only inside a very narrow, extremely selective band. The property I am referring to is known as selectivity. The generally accepted standard for gauging selectivity of a circuit is the range of frequencies inside of which the circuit experiences half power or greater. For this reason, the left and right boundary frequencies of this region are often known as the lower and upper half power frequencies, F1 and F2. They are also known as the cutoff frequencies, the band frequencies, or corner frequencies, depending on which industry jargon you're employing. Operating the circuit at any frequency inside this band would experience half power or greater. Operating the circuit at any frequency outside this band experiences half power or less. This is perhaps the most practical application of resonant circuits, even more so than developing electroshock weapons. Consider several senders broadcasting information on several different frequencies. By tuning a receiver to a desired frequency, everything unwanted is rejected and only inside that small band of frequencies is admitted, or shall we say, selected. You'd think that there'd be a symmetry between the lower and upper half-power frequencies, F1 and F2, such that they're equidistant from the resonant frequency, but they are not, and only in special occasions can we assume this to be true. 2 formulas can be used to solve for the lower and upper half-power frequencies, F1 and F2, the derivations of which I will not demonstrate because it is a mathematical goat show of epic proportions. I will, however, explain the general origin of these formulas. A condition of half power implies that source current is equal to the maximum current divided by square root 2. Why 1 over square root 2? You recall that power, among its many means of computation, can be calculated at any point on the selectivity curve as source current squared times the impedance. Peak power at resonance occurs because peak current flows through the resistor. This would be calculated as peak current squared times resistance. This yields a known maximum power condition, P max. If current happens to be 1 over square root times peak, or roughly 0.707 current peak, the power calculation yields 1 over square root 2 peak current squared times the impedance. 1 over square root 2 squared is half peak power. Get it? Any frequency resulting in current above 0.707 or 70.7% of peak would yield half power or greater. And any frequency resulting in current below 0.707 or 70.7% of peak would yield half power or less. What are these half power cutoff frequencies? I will skip the derivation because I don't have all day, but the lower half power frequency F1 can be calculated using this weighty formula, and the upper half power frequency F2 can be calculated using this similarly weighty formula. Notice these 2 formulas are almost identical, and only a small, easily overlooked negative sign differentiates the 2. Don't screw up the formula by overlooking the negative sign. For our original illustrated example, an application of the first half power formula suggests F1 equals 51.8 Hz. A subsequent application of the second half power formula suggests that F2 equals 84.9 Hz. Like I mentioned earlier, the half power region isn't exactly symmetric around the resonant frequency for this particular circuit because the lower half power frequency is separated from a resonant frequency of 66.3 Hz only by 10.5 Hz, whereas the upper half power frequency is separated from a resonant frequency of 66.3 Hz by 18.6 Hz. Let's check our work. If everything I've been saying is true, at either one of these half-power frequencies, source current should be our peak current times 1 over square root 2, or 0.707 times peak. Recall we observed a peak current of 1.2 amps. We should therefore expect a current draw of roughly 849 milliamperes at either one of these half-power frequencies. For the lower half-power frequency of 51.8 Hz, the complex impedance for the 12 microfarad capacitor will be 256 ohms at an angle of negative 90 degrees. The complex impedance of the 400 millihenry inductor will now be 156.2 ohms at an angle of positive 90 degrees. The total impedance will be the summation of ZR, ZC, and ZL. Substituting our given values yields a total impedance of 141.3 ohms at an angle of negative 45 degrees. Notice the negative angle indicates total impedance has a capacitive nature, as we might expect. Application of Ohm's law demonstrates source current at the lower half-power frequency will be approximately 849 milliamperes at an angle of 45 degrees. This verifies our earlier expectations. Note current leads by 45 degrees for this capacitive arrangement at the lower half-power frequency. Let's now examine voltage distribution within this series circuit at the lower half-power frequency. An application of Ohm's law demonstrates voltage across the resistor will be 84.9 volts at an angle of 45 degrees. Another application of Ohm's law demonstrates voltage across the capacitor will be 217.5 volts at an angle of negative 45 degrees. And finally, yet another application of Ohm's law demonstrates voltage across the inductor will be equal to 132.7 volts at an angle of 135 degrees. As previously, take a moment to weigh the consequences of operating at the lower half-power frequency, i.e. lower than the resonant frequency. Capacitive impedance went up. Inductive impedance went down. Total impedance seems to favor a somewhat capacitive nature. Source current goes down and starts leading supply voltage as we'd expect for a capacitive circuit. Finally, voltage distribution within the series circuit changed. Less voltage was dropped across the resistor and inductor, and more was dropped across the capacitor. In summary, at an excitation frequency below the resonant frequency, this circuit appears more capacitive. Importantly, given this is the lower half-power frequency, source current is roughly 849 milliamperes, as predicted, being 1.2 amps, a maximum current, divided by square root 2. I leave as an exercise to the viewer to solve for these same electrical properties at the upper half-power frequency of 84.9 Hz. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. At the upper half-power frequency of 84.9 Hz, note source current will be roughly 84.9 milliamperes at an angle of negative 45 degrees, i.e. 1.2 amps, divided by square root 2. Notice the negative angle indicates source current now lags supply voltage for this largely inductive arrangement at the upper half-power frequency. Again, take a moment to weigh the consequences of operating at the upper half-power frequency, i.e. something higher than the resonant frequency. Capacitive impedance went down. Inductive impedance went up. Source current goes down and starts lagging supply voltage, as we'd expect for an inductive circuit. Finally, voltage distribution within the series circuit changed. Less voltage was dropped across the resistor and capacitor, and more was dropped across the inductor. In summary, at an excitation frequency above the resonant frequency, this circuit appears more inductive. Importantly, given this is the upper half-power frequency, source current is roughly 849 milliamperes, as predicted, being 1.2 amps, i.e. maximum current, divided by square root 2. Moving on. Let's now discuss bandwidth and quality factor. The half-power or greater region between F1 and F2 is known as the bandwidth. For our particular circuit, it has a bandwidth of 84.9 Hz, minus 51.8 Hz, or 33.2 Hz. Another property associated with resonant circuits is something known as quality factor, sometimes abbreviated as QF. Explaining quality factor is like trying to nail Jello to a tree, and it'll take some time and repeat exposure for you to truly understand its significance. On a basic fundamental level, quality factor compares the reactive power exchange between the reactive elements with that amount of real power dissipated by the circuit. In its purest form, quality factor is calculated as the ratio of reactive power placed in storage over the real power. However, it can be calculated using a far easier method. Recall that power, among its many means of computation, can be calculated as current squared times impedance. If we wish to calculate the reactive power exchange between the reactive inductor and the capacitor, the top half of our ratio, we would square source current and multiply it times one of the reactive impedances, that of the inductor or the capacitor. After all, they're equal at conditions of resonance. Similarly, to calculate the real power dissipated by the circuit, the bottom half of our ratio, we'd square source current and multiply it times resistance. Note the like I squared terms in the numerator and denominator. I squared cancels out. We're left with quality factor equals the ratio of the reactive impedance, inductor or capacitor, whichever one you want, over the resistance. For our initial example series circuit at conditions of resonance, the capacitor and inductor each have an impedance of 200 ohms, whereas the resistor has an impedance of 100 ohms. Substituting our given values yields a quality factor of 2. This is a pretty crappy quality factor, but it gets the job done. Like I said, understanding the significance of quality factor will take some exposure. However, it needs to be stated up front that quality factor is a super handy cheat code for other calculations. Recall that in order to calculate bandwidth, we first had to calculate the lower and upper half-power frequencies using two super weighty formulas and then subtract them to find the difference. While this method does work, there's a much quicker method of doing so, where bandwidth is the resonant frequency divided by quality factor. Substituting our given values for our initial example series circuit directly yields a bandwidth of 33.2 Hz, exactly as we previously obtained without all the toil and tears. Additionally, quality factor can also be used to quickly approximate the voltage across the reactive components at conditions of resonance, where voltage across the reactive components at conditions of resonance is equal to the quality factor times the supply voltage. For our original series circuit, quality factor of 2 times the source voltage of 120 volts yields 240 volts as we previously attained, again without all the heartbreaking labor. Finally, when quality factor is determined to be 10 or greater, synonymous for a circuit with a super tight, very narrow bandwidth, it's relatively safe to assume that the lower and upper half-power frequencies are indeed symmetric and equidistant from the resonant frequency. This obviously wasn't true for our initial example. However, consider a series circuit employing a 40 ohm resistor, a smaller capacitor with a capacitance value of 6 microfarads, and a larger inductor with a value of 960 millihenries. Let's make this an illustrated example. See if you can determine the resonant frequency of this circuit and determine the electrical properties of this circuit at conditions of resonance, specifically total impedance, source current, and voltage across the resistor, capacitor, and inductor. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. An application of the resonant frequency formula demonstrates this circuit also experiences resonance at roughly 66.3 Hz. It makes sense. We double the inductance and halve the capacitance. As a result, the resonant frequency stays put at 66.3 Hz. The 40 ohm resistor presents a complex impedance of 40 ohms at an angle of 0 degrees. At the resonant frequency of 66.3 Hz, the 6 microfarad capacitor presents an impedance of roughly 400 ohms at an angle of negative 90 degrees. At the resonant frequency of 66.3 Hz, the 960 millihenry inductor presents an impedance of roughly 400 ohms at an angle of positive 90 degrees. As we expected, the capacitive and inductive impedances at conditions of resonance are equal and opposite to one another. Total impedance is the sum of ZR plus ZC plus ZL. Substituting our given values yields a total impedance to be 40 ohms at an angle of 0 degrees. As we expected, the capacitive and inductive impedance contributions cancel each other out at conditions of resonance, such that the total impedance appears to be only the resistive component. This represents the lowest impedance magnitude, and as such, we'll expect source current to peak. An application of Ohm's law demonstrates source current will be 3 amps at an angle of 0 degrees. Source current is in phase with supply voltage. Given this is a series circuit with a single path recurrent, it can be said 3 amps at an angle of 0 degrees flows through all three elements forming the series connection. IR equals 3 amps at an angle of 0 degrees, as does IC and IL. Let's now examine voltage distribution within this series circuit. An application of Ohm's law demonstrates voltage across the resistor will be 120 volts at an angle of 0 degrees. Another application of Ohm's law demonstrates voltage across the capacitor will be equal to an astronomical 1.2 kilovolts at an angle of negative 90 degrees. Finally, yet another application of Ohm's law demonstrates voltage across the inductor will be equal to an astronomical 1.2 kilovolts at an angle of positive 90 degrees. This is obviously a comically exaggerated example, intended to dramatically illustrate characteristics of series resonant circuits with large quality factor values, notably extremely high voltages across the reactive components at conditions of resonance. Speaking of quality factor, what's the quality factor for this circuit? What are the corner or half-power frequencies? And what's the bandwidth for this particular circuit? By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. The short and sweet quality factor formula demonstrates the reactive components have an impedance 10 times that of the resistive component, therefore the quality factor for this circuit is 10. The bandwidth is the resonant frequency divided by quality factor. Substituting our given values, we find an extremely small bandwidth of only 6.6 Hz. The high quality factor is indicative of a far more selective circuit, thus a smaller bandwidth. Let's now determine the lower and upper half-power frequencies. I suppose we could use the weighty half-power frequency formulas. However, given the circuit has a quality factor of 10 or greater, we are allowed to assume the half-power frequencies are perfectly symmetric about the resonant frequency. Given a 6.6 Hz bandwidth, 3.3 Hz to the left of the resonant frequency will be F1, and 3.3 Hz to the right of the resonant frequency will be F2. Substituting in our given values yields F1 to be roughly 63 Hz and F2 to be roughly 69.6 Hz. If you're hard-headed enough or had a lot of time on your hands, you could use the weighty half-power frequency formulas that are only slightly more accurate than obtained using this approximation allowed by a quality factor of 10 or greater, however at the cost of much, much more work. Note the resonant frequency of this circuit is the same as our original circuit. However, we observed a substantially different properties at resonance because this new circuit employed a smaller resistor, a smaller capacitor, and a larger inductor. For series resonant circuits, that's a surefire combination to increase the quality factor. At conditions of resonance, note the reactive components have much higher impedances than the resistor, and all elements experience a peak current of 3 amps. As a result, the reactive components at resonance experience extremely high voltage differentials, equal in magnitude, yet perfectly out of phase with one another. This is indicative of a substantial amount of reactive power being juggled back and forth between these two reactive elements. As we did with the original circuit, one could perform a frequency sweep analysis of this modified circuit, plotting source current magnitude as a function of frequency. Doing so, we observe the following behavior. It's perhaps worthwhile to compare this new modified circuit, incorporating a smaller resistor and a smaller capacitor and a larger inductor with our original circuit. As did the original circuit, only at conditions of resonance, in this case 66.3 Hz, does current peak. Only this time it does so in a particularly dramatic fashion. Only inside a very, very narrow bandwidth, in this case 6.6 Hz wide, does our current ever reach roughly 0.707 or 70.7% of peak current. Only inside this highly selective region, between 63 Hz and 69.6 Hz, will the circuit experience half power or greater. Series resonant circuits with smaller resistors, larger inductors, and smaller capacitors have higher quality factor values, smaller bandwidths, and as a result are more selective. Conversely, series circuits with larger resistors, smaller inductors, and larger capacitors have lower quality factor values, larger bandwidths, and as a result are less selective. To reiterate this concept, consider these 3 plots of source current as a function of frequency for 3 different circuits. The one in the middle is our original series AC circuit, consisting of a 100 ohm resistor, a 12 microfarad capacitor, and a 480 millihenry inductor. At the resonant condition of 66.3 Hz, current peaks at 1.2 amps. As a quality factor of 2, an asymmetric bandwidth of 33.2 Hz between 51.8 Hz and 84.9 Hz. At resonance, we observe voltage across the reactive elements to be 2 times the source voltage. The plot on the right is a modified series AC circuit consisting of a smaller 40 ohm resistor, a smaller 6 microfarad capacitor, and a larger 960 millihenry inductor. At the resonant condition of 66.3 Hz, current peaks at a much larger 3 amps. It has a quality factor of 10, a bandwidth of 6.6 Hz, symmetrically distributed between 63 Hz and 66.9 Hz. At resonance, we observe voltage across the reactive elements to be 10 times the source voltage. The plot on the left is a modified series AC circuit consisting of a larger 200 ohm resistor, a larger 24 microfarad capacitor, and a smaller 240 millihenry inductor. This circuit is dirty, manky smelling, and appears to have a fine coating of moss growing on it. Given these component values, we'd also expect it to experience resonance at 66.3 Hz, albeit a resonance of significantly less pizzazz than the other two. Plotted on the same vertical scale as the other two, the plot of source current as a function of frequency looks as limp as an earthworm caught in a rain puddle, and it's hard to tell what source current is actually doing. Even if we zoom in, we find source current weakly peaks at a resonant frequency of 66.3 Hz, however at a much, much smaller value of 600 milliamperes. It has a quality factor of 0.5, meaning at conditions of resonance, the impedance of the reactive components are only half that of the resistor. In this case, half of 200 is 100 ohms. This implies the circuit has a wide bandwidth of 132.6 Hz, meaning it's super permissive, i.e. extremely non-selective. Given such a low quality factor, the bandwidth is obviously asymmetric, and we need to resort to some heavy lifting to determine the lower and upper half-power frequencies. I'll save you the trouble and solve them myself. The lower half-power frequency F1 is approximately 27.5 Hz, and the upper half-power frequency is 160.1 Hz. Anything inside this wide, extremely non-selective range will experience half power or greater, and even that won't be as much compared to the other two circuits given such a small peak current. Finally, at resonance, we would expect voltage across the reactive elements to be half the source voltage, in this case 60 volts. Note for this lackluster circuit, the voltage across the reactive components isn't nearly as high as the other two given its low quality factor value. In summary, component levels dictate not only the resonant frequency, but also the performance at conditions of resonance. I kind of illustrated everything at once. However, we can look how the resistance value and the ratio of the inductor and capacitor independently influence performance at resonance. Consider a series resonant circuit with a fixed inductor and capacitor. With a resistor of a given value, we might expect the plot of source current as a function of frequency to look like this, where current peaks at the resonant frequency and it has a given bandwidth. If we kept the inductor and capacitor the same but decreased the resistance, the resonant frequency will remain fixed. However, the smaller resistor would permit more current to flow. As such, we might expect the plot of source current as a function of frequency to look like this, where current peaks at a higher value. As a result, the circuit has a higher quality factor and a smaller bandwidth. Conversely, if we kept the inductor and capacitor the same but increased the resistance, the resonant frequency will remain fixed. However, the larger resistor would permit less current to flow. As such, we might expect the plot of source current as a function of frequency to look like this, where current peaks at a lower value. As a result, the circuit has a lower quality factor and a larger bandwidth. In summary, series circuits with lower resistances experience higher current at resonance and have higher quality factor and tighter bandwidths. Let's now keep resistance the same and consider how the ratio of the inductor and capacitor influences the performance at resonance. As we observe, circuits employing larger inductors and smaller capacitors exhibit higher quality factor values, and circuits employing smaller inductors and larger capacitors exhibit lower quality factor values. Consider a series resonant circuit with a fixed resistor and a given inductor capacitor value. We might expect the plot of source current as a function of frequency to look like this, where current again peaks at the resonant frequency and it has a given bandwidth. If we kept the resistor constant, but increased the value of the inductor and decreased the value of the capacitor by the same amount, i.e. we increase the inductance to capacitance ratio, the resonant frequency and peak current will remain fixed. However, the larger inductor to smaller capacitor ratio would tighten the bandwidth considerably. Conversely, if we kept the resistor constant, but decreased the value of the inductor and increased the value of the capacitor by the same amount, the resonant frequency and peak current would remain fixed. However, the smaller to inductor to larger capacitor ratio would spread the bandwidth out quite a bit. Like I said, the significance of quality factor is a little difficult to conceptualize at first, but I'm hoping these graphs and the previous exercises illustrated how quality factor conveys a measurable indication of how selective a circuit is or is not, and how component level values not only specify when resonance occurs, but also the performance at conditions of resonance and at conditions of other than resonance. All right, that's about it for today. Yes, I have left a lot unsaid about resonance, but as I said in the beginning of this lecture, I categorically refuse to wrestle that dirty, dirty pig. This being said, with this lecture now in your pocket, you are probably well prepared to dive into the dirtiest pig pen of your choosing and give it a go if you feel so inclined. As for me, I am done with this pig, and I'll just sit back and watch you get muddy. Have fun. In conclusion, this lecture examined fundamental properties about series AC resonance. We learned series AC circuits experience resonance at frequencies when the capacitive and inductive impedance components cancel each other out. At conditions of resonance, impedance magnitude valleys, and source current peaks. Additionally, we examined the significance of the quality factor on the selectivity of a given circuit and examined the means of calculating bandwidth and half-power frequencies. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.